Hello friends, welcome to my YouTube channel. Today in this video I am going to discuss countability of rationals using Cantor's method. An infinite set is said to be countable if its elements can be listed in the form of a sequence. That is, if there exists a one-to-one correspondence, that is a bijection, between the set of natural numbers, that is 1, 2, 3, 4, 5 and so on, and the given set. In this video, we discuss the countability of the set of all rational numbers using a popular method due to Georg Cantor. A rational number is actually a quotient or a fraction of the form a by b of two integers, namely a numerator a and a non-zero denominator b. Cancelling out the greatest common divisor of the numerator and the denominator, one can always write a rational number uniquely as a quotient or a fraction of the form m by n of two relatively prime integers m and n with n greater than or equal to 1. Relatively prime or co-prime means that the greatest common divisor of m and n is equal to 1. GCD of m and n equal to 1. And such a quotient or a fraction is said to be in its reduced form. So, reduced form means the numerator and denominator will have GCD 1 and denominator is greater than or equal to 1. Okay. Note that all the rational numbers can be arranged in the form of an arbitrarily large array which may be regarded as a matrix of infinite size as follows. And one more thing, whatever I am going to show you, you will find some encircled fractions which are not in the reduced form and they are to be omitted, ignored. So, what is the arrangement? First we write 0. 0 can be written in the reduced form as 0 by 1. Then we write all the integers, all the positive integers. So, positive integers 1, 2, 3, 4 etc. can be written as 1 by 1, 2 by 1, 3 by 1, 4 by 1 like this. Next we write negative of all the integers, negative of whatever we have written in the first column. So, it is minus 1 by 1, minus 2 by 1 and so on. Then in the third column we write all the rational numbers whose denominator is 2, and here the encircled entries appear for the first time, and this entry is encircled because it is not in reduced form, and its reduced form actually appears in the top left corner, this one. Here you will find this 2 by 2, and more precisely 2 by 2 is 1. So, this is actually your 2 by 2. Similarly, 4 by 2 appears in this rectangle, and more precisely 4 by 2 is actually 2 means 2 by 1. So, it is appearing here. Okay. So, we avoid duplication. So, all the rational numbers, all the fractions which are not in the reduced form are to be avoided, and we have encircled them. Okay. Next, in the next column we write negative of whatever is written in the previous column. Then we write all rational numbers whose denominator is 3, and here also once again you see 3 by 3 is avoided, ignored, because it is 1 by 1 already appearing here. Then negative of this column. So, in this way all the rational numbers can be written in this arrangement, whether positive, negative or 0. More precisely, if you want to see, suppose I consider a number say m by n. So, because it is now first of all it is a positive rational number. So, numerator is m. So, somewhere in the mth row it will appear, and denominator is n. Now, 1 appears here in first and second column, 2 appears in third and fourth column, 3 appears in fifth and sixth column. So, n will appear in twice n minus 1 and twice nth column. So, since it is positive, so it will appear in twice n minus 1th column. So, 2 n minus 1. So somewhere here m by n will appear. Okay. And if it is a negative minus m by n, so it will appear somewhere in the next column. So it is here in twice n. So it will appear somewhere here as minus m by n. Okay. So in this way, all the rational numbers, whether positive, negative, or 0, can be found in this arrangement. Okay. So next is just to read these numbers one by one. Okay, sequentially. So how can you do this? One option is you can start from 0 and go to 1 by 1, then minus 1 by 1, then you can go to half also, and then this one is to be avoided. Then you can go to this, then go to this, then go down, then this, then this, then this, then go up. This is to be avoided, then this, and then this. Okay, then this, and then this is to be avoided. Then come here. Okay, sorry, this is also to be avoided. Then this, then this. So in this way, you can see whatever is to be avoided are encircled. So encircled entries are to be avoided. So this is to be avoided. So in this way, everything can be covered like this. Okay. Other option could be like this. You simply first you read 0 and then you, diagonally, that means, so then you read 1, then you read these two entries, then you read these three entries, then you read these four, rather three entries, this is avoided, then you read these entries, then you read, okay, this one also avoided, then you read these entries. So in this way you can read the entries. This is first, second, third, fourth, then fifth, sixth, seventh, eighth, 9, 10, 11, 12, 13, 14, okay, 15, 16, this is to be able to 17, 18, 19, and so on like that. Okay. So in this way, what happens? All the rational numbers may be listed in the form of a sequence as 0 by 1, 1 by 1, 2 by 1, minus 1 by 1, 3 by 1, minus 2 by 2, and so on. And here you can see all the rational numbers, whether they are positive, negative, or 0, appear in this sequence. Okay. And hence the set of all rational numbers is a countable set. Hope this video will be useful for you. Thanks for watching.